So in this video, we're going to do some problems dealing with limits of two-dimensional functions, or two variable functions here. This is going to be a little bit more complicated than a limit of a one-variable function. Here we'll see some examples here. So if we're going to start off with finding the limit as xy goes to 0, 0 of the function x squared y over 1 minus xy minus x squared. Now, similar to when you have a one-variable function, the first thing you want to do generally is just try and plug in 0 for x, 0 for y, the corresponding x and y values, and see what happens. So here, what we get, if we do that, you get, let's see, we're going to hope this is 0 squared times 0 over 1 minus 0 times 0 minus 0 squared. This works out to be 0 over 1, which we can evaluate just fine. That's just 0. So as long as this function is continuous, which basically all the nice functions we deal with are, except at some boundary cases here, we can just plug the values in and you get a 0 here. So this works out fine. So we found the limit is 0 here. Just graphically what that's going to look like here. Here's a picture of this graph, or this function graphed here. That red dot is really the origin at height 0. You can see sort of near the origin, nothing really crazy is happening. Things are smooth here. We can sort of approach that point in any direction and end up sort of at the same height. There's some kind of crazier stuff over here, but that's not near the origin. We can make a sort of a ball around the origin and not have to worry about that. So that's really the idea here of what's going on. I'll leave that there. Okay. Let's do the next one. That one pretty straightforward. Next one, things are going to get a little bit worse here. I'm going to just try and plug in 0, 0 again. When you do that, you're going to get 1 plus 0 squared times 0 over 0 times 0 minus 0 squared. This goes to, let's see, I get a 1 on top, and then 0 minus 0 really has 0 on the bottom. So 1 over 0 here, well, so I always have something close to 1 on top and something that's really, really small on the bottom. That means I'm going to get a value really, really big. So this goes to either plus or minus infinity. I don't really care. In either case, the limit does not exist. So again, another one, not so bad to do, a little bit harder maybe to comprehend. A picture of what's going on might help here. So we can drag this, make it bigger. So here's this function here. What you can see is our denominator was x times y minus x squared. That's going to have zeros. I can factor out the x. So let's just go back here and say our denominator. We had x, y minus x squared. That's our denominator. That's x times y minus x. So we'll have zeros when y equals x or when x equals 0 here. So this is probably x equals 0. Here you can kind of see that ridge. Here's y equals x. And those both go to infinity here. And anytime you get close enough, you're going to sort of hit one of those and go to infinity. But also it turns out, the way we did the calculation here is no matter if you come in some other direction, you're also going to sort of go to infinity, which is kind of harder to see exactly what's going on here. But even if you approach this way, you'd end up going to infinity here, but not in quite as an obvious way as the y equals x and the x equals 0. Okay. Next one here, here's where things start to get maybe more interesting here. So this one, I've got a limit as xy goes to the origin again, to 0, 0, of the function xy over x cubed plus xy. Now, I can plug in the 0 over 0, or sorry, 0 times 0. I get 0, sorry, plug in 0 for x, 0 for y. I get 0 times 0 over 0 cubed plus 0 times 0. If you put this together, you get 0 over 0, which is sort of our classical indeterminate. This could have a limit, could not exist. Could go to infinity, could go to 0, could go to any number in between. Might not even, kind of go in one direction at all. May go in different directions from different paths here. So this is more the interesting case. So what we're going to do, let's look at the graph of this particular function. So it's this guy here. What we're going to do here is we're going to try, the origin's somewhere over here. We're going to try and approach the origin from sort of a path going maybe like this, or a path like this, or a path like this. And the question is, do all these sort of approaches have the same height here. Really, it's something that's required for this to be continuous here. I could even approach along all lines and have a function still not continuous, or sorry, still not have a limit. So I could have a limit along each line, but still not really have a limit. What I really need is that if I get in some sort of circle really close to the origin here, that all the z values are close to each other. It's a little bit hard to tell because maybe I just haven't zoomed in enough. Here my range on my x's and y's goes from -2 to 2. Here, maybe if I went from -0.001 to 0.001 for each of those, we'd get functions that are all sort of, or values that are all close together here. So that's one way to go. But you can actually show that that's not going to happen here by picking a couple paths. So one path I'm going to pick here, I'm going to pick the path y equals 0. So along y equals 0, I'm going to just approach with the points where y equals 0. So let's see, I think this is going to be really along this line here. You've got it rotated a bit. I believe this is the y equals 0 here. And so I'm really going to approach going along this sort of surface here. And the question is, where am I, what sort of height am I at the origin? So we can calculate that by plugging in just y equals 0 first. And then this limit here really becomes the limit as x goes to 0 of, well, x times 0, that's just 0, over x cubed plus x times 0, that's 0. So this is the limit as x goes to 0 of 0. So if x isn't 0, this is actually just a 0 here. So that limit is 0. So what we're saying here is that if we approach anywhere along the line y equals 0 in either direction, we get a limit of 0. Now, on the other hand, if I do, let's just do a general, how about y equals x here? Let's do y equals x. Well, when you do that, then our limit, let me switch to another color here. Let's do the y equals x in green, I guess. When I take that path, what I get for this limit here is I get a limit as now, well, I'm going to say x goes to 0. So that's going to force both y and x to go to 0 because y is the same thing as x. And I'm going to get x, where I see the y, I'm going to put an x. So x times x times y is x times x, in this case. And then I get x cubed plus x, and then that second y I also put an x. So this is a limit as x goes to 0 of x squared over x cubed plus x squared. And I'm going to divide the top and bottom by x squared, or maybe factor out an x squared from the top and bottom. And that's going to give me 1 over x plus 1. And then as x gets really, really small, this bottom is going to go to 1, 0 plus 1. And this whole thing is going to just give me 1. Now, note, the key thing here is we did the path y equals 0. We got a limit of 0. We went along the path y equals x, and we calculated we should get a limit of 1 here. Because these two do not match, I found two paths that do not match, this means that the limit does not exist. So if the limit existed, that means that all paths would have to agree. Now, just because I agree along two paths, that doesn't mean the limit exists. There might be some other path I didn't think about where they'll sort of get a different limit if I go along that path. And so what you could see here, let's just go down, I've got sort of a diagram with the paths drawn here. What I've got here is this red, I think, is y equals 0. The green, I believe, is y equals x. Again, maybe I should rotate it like this so it looks more like you're used to in terms of, whoops, x and y here. And what happens here is they sort of both follow along. You see this green goes up and then down and kind of cuts through here. What you get, if you look at this, let's see if we can find a good angle of it. We need to be over here. It's a little bit hard to see here. But if you zoomed in enough, maybe this one, you can see this green is sort of up here, but the red is down here. So there's sort of a gap between these two. That's the 0 to 1 gap here. So there's a gap between those two. That means the limit doesn't exist. Now this orange guy, this is actually y equals x squared. That one actually goes to a half. You could plug in here. So let's just do that. If you do y equals x squared, what you get here for our limit is you get a limit as, again, I would say x goes to 0. X times the y becomes an x squared. I get an x cubed plus x times another x squared. This is a limit as x goes to 0 of x cubed over x cubed plus x cubed, 2x cubed. That gives us even a third value here of a half. And there may be other values as well. Really, you just need 2 that are different, but 3 sort of, I don't know, shows it really, really well, I guess, in some sense. Okay, next one here. I'm going to deal with the limit as xy goes to 0, 0 of x minus y over 3x plus y. So this one, I'm going to choose a path y equals 0 and just see what happens. So it's a nice path to start with here. What I get is let's see, if I plug in y equals 0, I get a limit as x goes to 0. The y's drop out, and I get x over 3x. Well, that's just 1/3, so that limit is 1/3. Now, if I switch this up and use x equals 0, and plug x equals 0 into my original limit, it's going to turn into a limit as y goes to 0. Now the x's drop out, and I get negative y over y. That's going to be negative 1 for every y not equal to 0, so the limit's negative 1. Now again, I know the limit, this here, does not exist. And the reason for that is we got 2 values that just do not match here. Another technique that can be nice to use here, let's maybe go up to the previous one and show this. I think it's a little more illustrative. So when you have the xy times x cubed plus xy, let me do this in orange. What you could do is instead of doing y equals 0, y equals x, maybe x equals 0, y equals 2x, a bunch of different lines, a lot of times you can just plug in y equals mx into this original thing, and then you get the limit as x goes to 0. Here you get x times mx, where m is just some slope, x cubed plus x times mx, and so you get a limit as x goes to 0 of mx squared over x cubed plus mx squared. Divide top and bottom by x squared, and what you get is 1 over, sorry, not 1, m, make that a little nicer, m over x plus m. Well, as x goes to 0, this goes to m over m, which as long as m isn't 0, that's going to go to 1 here. Note, if m was 0, you get 0 to 0. It turns out that the limit is 0. We did that already. Y equals 0. So you get a limit of 1. What this says is if I approach along any line that's not y equals 0 or x equals 0, which doesn't have this form, I will get a limit of 1 here. Note, y equals x was a special case. So that sometimes this is really nice to do because you'll get a formula in this limit here that depends on m, and that just tells you right away, like, well, plug in 2 different values of m, you get 2 different values for the limit, which means the limit does not exist. Okay, next one here. We can do the limit as xy goes to 0, 0 of natural log of 3 minus x over x squared plus y squared. Again, I'm going to start off just trying to plug in 0 and 0. So I get natural log 3 minus 0 over 0 squared plus 0 squared. It goes to log of really 3 over 0. Now look, this is going to go to log of infinity. In some sense, I don't really care if that's positive infinity or negative infinity. Actually, it's going to be positive infinity. Well, for log, I do care, first of all, because log's only defined for positive value, or yeah, for positive values. So I can't plug in negatives at all here. So in particular, like negative 100 doesn't work here. But look, 3 minus x will certainly be positive. It'll be, 2.9999 at the lowest. X squared and y squared are both positive. So this whole thing inside is positive. So this checks out. And this goes to natural log of infinity, which goes to really infinity here. So it's telling me that this function just gets really, really big as xy goes to infinity, and that's one case where the limit does not exist. Now this one has maybe a little bit nicer looking picture. You look at the graph. Whoop, that was the last one we did, actually. Just skip that there. There's the two sort of x equals 0, y equals 0 in the previous one. Here you can definitely see the 2 lines have a gap there. Now the one we did just now, this is really what our picture looks like. We have this circle in Mathematica. What it's doing is plotting points, and it didn't get any close enough to the origin where that would evaluate. And so it's just sort of going up into a cone. And what our limit, being infinity, shows is this cone is going to sort of go up to infinite height. It's going to keep going and going and going if you get closer and closer and closer. Okay, last one here. We've got x squared y over 1 minus square root x squared plus 1, xy's limit as xy goes to 0, 0. So if you plugged in 0 for x, 0 for y, you'd get 0 over 1 minus square root of 1, which is 1 minus 1. You get 0 over 0. This would be undetermined. And so what you would do is you might look at the graph. Here's the graph of this. Now that looks all nice. There's nothing kind of crazy going on at the origin. So I suspect the limit exists. You might be able to figure out what you think the value is. But sometimes that, sort of nothing, I don't have sort of this holes here essentially, or crazy ridges or anything, tells me I expect the limit to exist. And now we're going to do some algebra to actually show that. So what I'm going to do here is I'm going to just work on, well, let's just say this is the limit as xy goes to 0, 0 of, I have this 1 minus square root x squared plus 1 on the bottom. One trick here, I think this is more kind of a, well, I'd say a Calc 1 trick, but maybe somewhere else you've seen that, is to take this, whoops, not square root yet, take the 1 minus square root x squared plus 1 and multiply the top and bottom by what I'm going to call the conjugate here. And that's you switch that minus to a plus. So instead of 1 minus square root x squared plus 1, do 1 plus square root x squared plus 1. The reason you would do that here is you're trying to manipulate really the expression. Whoops, sorry. We're trying to manipulate the identity here that if I do a minus b times a plus b, this is a squared minus b squared. Here, so here if I square these, I have a is 1, b is square root of x squared plus 1. If I square these, the square root will go away and things will look a little bit nicer. So that's really what we're hoping for. So let's just execute this. So our top is x squared y times 1 plus square root x squared plus 1. Our bottom is now 1 times 1, that's 1, minus the square root squared, that's minus x squared plus 1. And so what we get is a limit as xy goes to 0, 0. We get x squared y over, I keep forgetting my 1 plus square root x squared plus 1. On the bottom, I get 1 minus the plus 1. Those cancel. I'm just left with x squared. So now, as long as x is not 0, now this is a little bit of a concern because I could approach along x equals 0, but it turns out if x is 0, well, anything with x equals 0 is going to make my function's denominator 0, means that won't be in the domain of the original function, so we don't really need to consider points where this denominator is 0, that is points where x is 0. It's sort of for the limit definition, it's sort of only concerned about the points in the domain of the function. Anything with x equals 0 will not be in the domain, so I can really cancel the x squared without having to worry about that. And I'm just left with y times 1 plus square root x squared plus 1. Now, I can plug in 0 and 0 into this, and I get 0 times 1 plus square root 0 squared plus 1. This gives me 0 times 1 plus 1, which is 0 times 2. I don't even know why I'm bothering trying to simplify this. It's 0 times some number. That's just 0. So our limit is 0, and you can look here on the height, here at the origin, whoops, well, you have the 0 height there. That seems sort of plausible there. So that height is 0 there. And that just checks out. Okay, so that's going to end our video here.